All right. Hi, everyone, and welcome to our second live episode of Dark Chatter. I'm Zachary Picker from the University of Sydney, and today we have a special guest, Giovanni Pierobon from the University of New South Wales. And he's going to be chatting to us about his new paper with a bunch of collaborators called Simulations of Axion-like Particles in the Post-Inflationary Scenario. So maybe you could just start by giving us some background on yourself. What kind of research are you interested in? What have you worked on so far?
Sure. Thanks, Zach. Well, I've been interested in axions since my master's project back in Europe a few years ago. I was introduced to axion physics from a model theory point of view, and I was studying the production of axions in the early universe through thermal, in a thermal like background, so through couplings with the standard model particles. But then, as you know, axions are interesting because of the fact they are very interesting dark matter candidates. So I started to look more into it, to these dark matter scenarios. And there's two different scenarios in the literature, and these are depending on the scale of inflation. And in the scenario that we're interested in, the post-inflationary scenario, there are several open problems that don't have an answer yet. So it got me interested into, first of all, looking into the literature, what it takes to do this kind of simulations, which are required to solve these kind of problems. And it was almost a year long of literature reading and getting familiar with the scenario. And then we ended up looking at these numerical simulations.
Okay, so set the scene for what your paper is. Imagine you're writing like a literature review of your thesis. You're already up to there. How do you like lead into what you're about to do?
So I guess as I established, we're looking at the cosmological simulations of axions, but in principle we extend what is the status of this field of research by going into axion-like particles. So we generalize this QCD axion model, which has a particular model characteristics, and we extend it to more generic class of phenomenological particles that can have any coupling with standard model. In our case, axion-like particles are any kind of particle which is feebly coupled to the standard model. And they can be looked into a parameter space of this sort. So Kieran put up a very nice and updated plots where all these axion-like particles live in. And in particular, in the vertical axis, we have a coupling to photons in this case. So there are several types of plots depending on the coupling to particles. But in this vertical axis, we always have the inverse of the axion decay constant. This is a parameter where the axion is born, or the axion-like particle is born. And on the horizontal axis, we have a very wide range of masses that can be probed. And the QCD axion is just one example of these axion-like particles, and as a precise parameter space, which is this yellow band, which is diagonal. But in general, like experimental searches are aimed to, as I said, a very wide class of phenomenological particles of this sort. So as I said before, we're aiming to not only simulate the QCD axion, but a more general axion-like particle, which is important for indirect searches and future direct searches on a general scale.
Is there a particular reason to care about these axion-like particles other than just, we have lots of space on the plot to fill, or is there some kind of deeper, theoretical reason I should care about them?
I guess it depends who you ask. People in
I'm asking you.
Oh, I guess you know that this parameter space can be probed with our experiments, and they're very clever in doing so. And if you can exclude or detect something, then why not? So this parameter space, as you can see, is very wide, and it's very difficult to touch this yellow line, which is the less uncertain line, because it comes from an inconsistency in the standard model, so the strong CP problem, right? So axion-like particles are not really solving, in general, they're not related to the solution of the strong CP problem. But if you can probe the existence of such particle, then why not consider those?
So you're saying that particle physics is just like coloring in. Maybe we should make like a colorable version of this as like a kind of children's activity. Then we wouldn't even have to do any experiment.
Well, yeah, in a sense, you can say that.
Okay, so tell me what you actually did. What was different in your research than what had already been done?
Okay, so first of all, I want to give you a background of what are the main issues that are still open so far. So in the post-inflationary scenario, this scenario is in principle can be you can predict the abundance of cold axions. So we're looking at dark matter first of all. You can predict the abundance of axions. However, it's very complicated because this scenario is riddled with topological defects, which are highly nonlinear configurations, and they're very complicated in a cosmological setting. So estimating the dark matter abundance has several problems that don't have an answer at the moment. The first being the large separational scales between the formation of the axion field and therefore the strings, which are the topological defects, and the time by which they're getting destroyed. And it's a very large separational scale, as I said, and we cannot computationally solve all those scales. So this is one of and requires therefore a large extrapolation. The second problem is the topological susceptibility uncertainty. So when the axion mass becomes cosmologically relevant, which is when the axion field becomes non-relativistic, we actually have an uncertainty on how fast the axion mass is growing already at the QCD axion level. And then other several problems like the domain wall number for if the number of domain walls is larger than 1, and a late time in cosmology, the survival of axion mini classes which are forming in this post-inflationary scenario. And we're focusing on this second problem here. So first of all, we look what if we take the parameter that defines the topological susceptibility, or how much the axion mass is growing, how fast it's growing in cosmology, as an external parameter. And this leads us to give us an opportunity also to extend to axion-like particles, because we could have any generic axion mass growth in any particular model. Of course, everything is model dependent, but it also includes the case where the axion mass is constant. So you just have a bare mass in the Lagrangian, you just have a pseudo-scalar particle, which is fibly coupled with the model, and it can be dark matter. So what we do is we perform a series of simulations with a very large resolution. This is done using a public code that was previously developed by one of our collaborators. And we do this simulation on computational facilities, both at a local level at the university and the national level. And we study, as I said, this parameter dependence. So in one line, we study the dependence of the axion mass growth on a cosmological setting.
So you're running like a kind of simulation of the axion dynamics as the universe grows. What kind of result are you looking for at the end? Like what is the final thing that you come to, or that you were trying to come to?
Yeah, I guess we have two main things that we want to look into. First of all, how many axions we can actually produce. So in a sense that for the QCD axion, for example, it could allow you to determine what is the value of the axion mass that give us all the dark matter. It's a very precise estimation. And on the other hand, we want to also estimate what is how the substructure forms in the box, and that is important, especially at late time when, as I said, mini clusters are forming, and we want to understand how many of these axions that are cold survive into these bound structures and can be actually probed by direct detection nowadays. And in these two aims that we have, we will look at the fact that changing this parameter n matters quite a lot. So stimulating with n equals 0 or n equals 6 or 7 or 8 QCD axion values, it is very different, both in terms of the efficiency, so how many axions are actually produced. So that is relevant for the dark matter abundance, and what is the level of substructure, how much power do we have at what scales, and that really changes a lot varying n.
So how did you decide what values of n you were interested in? Is there like some kind of deeper reason, or is 6 just your favorite number? Or
okay, so in the QCD axion literature, you have various approximation to find the value of n, but they're all valid either a large temperature or a larger temperature than the QCD phase transition or smaller. So there's actually an uncertainty. And I guess the most reliable result comes from lattice QCD simulations, and they have a range between 6.5 and 8. Actually, n equal 8 was estimated back then in the 70s with the instanton approximation. So it's a semi-analytical computation. So I would say that at n larger than 6, you're tending to QCD axion values. Between 0 and 6, it's purely academic. There's no reason at all. But right. n equals 0, as I said, it's just a simple bare mass in the Lagrangian is very relevant for most of the literature.
Yeah, as soon as I asked that, I noticed you have a little plot on the corner there with exactly what you just explained to me. So you mentioned that you were looking at structure formation, and as I was reading your paper, you mentioned a lot about this thing called an axion, which I don't think I'd ever heard of before. Not to be confused with just the regular axion.
Exactly. Yeah, that's
something like new, or am I not up enough on the literature? Can you explain it to me?
Okay. The term axion was actually coined in the 90s by Koben Kachov.
Oh, I wasn't born yet, so I understand.
No, I mean, yeah, they were the first one to discuss this structure. So we're talking about what happens at the last end of the simulation. So we start. I give you a little bit of a background. What we see in a simulation, we go through a string network and a massless axion at a very early time. Then when the axion mass becomes of order of the Abel scales, then we have the formation of domain walls that in our case will pull the string and destroy the whole system. However, in the destruction of those walls, as you can see, they have a surface density in the second plot. They see the formation of these large over densities that are called axions. And these axions are similar to oscillon solution of a Sine-Gordon equation. So the Sine-Gordon equation is just a Klein-Gordon equation with a sine term instead of a linear term. And they are sustained. Sorry to skip this. They're sustained by the self-interaction of the QCD axion or the QCD potential. Sorry, of the axion potential. So as you expand this cosine potential, you have a mass term, and then a leading order you have a negative field to the 4 term. Okay, so this configuration are sustained by the self-interaction, which acts as an attractive force. So we see at the end of our simulation, we see this configuration forming that are quite interesting in the dynamics, and their distribution and characteristics, the properties, if you want, the profile of these things change considerably, changing the index n.
So wait, what's the difference between an axion and an axion mini cluster?
So an axion mini cluster is a gravitationally bound object that is actually the result of a large over density seed, and these large over density seed are also given by the axion at the end of the simulation. While these axions are just are sustained by the self-interaction, so there's no gravity yet. The self-interaction terms are actually dominant with respect to gravity at the end of the phase transition. And as I show here, in this configuration, there's a competition between the gradient pressure and the self-interaction, which is highly nonlinear when this configuration reaches the axion Compton wavelength. So when the size of these objects are the inverse axion mass. So it's also a source of uncertainty for our simulations, being highly nonlinear, and that definitely something that we'll look more carefully in the future.
So how do these axions depend on this n, your temperature dependence?
Okay, so if you look, for example, at a Gaussian lamp of axion in your simulation, you can see that if you look at the configuration, that the energy configuration, it will have a mass term, and then, as I said before, a gradient term and a self-interaction term. And we can define a critical value of the axion field, so the value of the amplitude, so this theta c, above which self-interaction wins, so we have an instability, and below which we have a stability region, and the axion doesn't collapse. And turns out that in a cosmological setting, this instability region is likely to develop for an index n larger than 2, as you can see in this in the last equation here. So it's proportional to the tau, the cosmological time, to the power n minus 2 divided by 4. So that means that for QCD axion, for example, where n is 7 or 8 or 6, it is very likely for this configuration to reach an instability and decay by emitting relativistic axions. As you can see in the plot of the bottom row, the second plot, you can see those spherical waves being emitted by this configuration. However, what we see in the simulation is that this configuration is likely to seed smaller axitons at later times. So they're very resilient, they're very long-lived, these objects. And on the other hand, if you look at the top row at n equal 1, this axion reach a stable configuration because it's not falling into this instability region since the gradient pressure is dominating.
So, okay, I've been asking you to just explain things to me because I don't know well enough. But what do you think is the most important result of your paper? I mean, what are you most excited about?
Okay, I'm very excited about the results on the dark matter, and we see in this plot the axion number density. So we count the number of axions, at the end of the simulation, and we see that as we vary this index n, we get much more axions for smaller n. Now we want to modify the linear misalignment contribution, so the contribution of axions that you can do analytically in the coherent oscillations around the potential, and we want to see if the presence of strings and walls enhance this relic abundance of axions. And it turns out that we have an enhancement for n equals 0 and 1, for example. There's more axions produced and then misalignment due to the decay from cosmic strings and domain walls. And at large values of n, instead we have this counterintuitive result where we have even less than misalignment. But this is because the linear misalignment calculation is a statistical average, but doesn't really take into account how much the axion mass is growing. So in here we present for the first time, at least to our knowledge, how much axions are produced due to cosmic strings and walls for n equals 0 and for any kind of n which is not in the QCD axion range. So I guess this is a first step towards a better understanding of even axion-like particles, because if you have a model with an axion-like particles, usually people just consider the misalignment contribution because they don't do the full simulation. So in this case, we give first of all a clear picture that varying this index n matters a lot. I think this is already an important result.
So you put this paper out 3 days ago or something, right?
Yeah, last week.
So who do you want to read this paper the most? Do you want experimentalists to know about this, or cosmologists, dark matter people?
I guess it's relevant for any research group which is interested in axions in a cosmological setting. So as you said, experimentalists are very keen to this kind of results because they want to build their experiments where theories or numerical results say that it's interesting to see. Especially for haloscopes, because they look for a specific narrow range of frequencies, or if you want axion mass. So you want to know very precisely where to look before you start building your experiment, if you can probe some parameter space area. But in general, I would say anybody who's interested in cosmological simulation, which is a very fascinating topic, according to what I think. Yeah.
So which part of this paper or this research were you most directly responsible for? Do you want to brag about a particular thing that we would never have realized otherwise?
I guess I don't want to brag about anything in this.
This is your space to brag. I've told you to brag.
I guess we have some very nice visualization, which allows us to really understand how different it is from simulating different n scenarios. So I guess the first thing that we've done is looking exactly at the snapshot of the energy densities or the field configuration to actually see how different it is changing this parameter. And we actually put a lot of plots in the paper. We also linked some animations on YouTube, and you can see that already at the visualization level, you can spot the difference.
Yeah. So I guess that's probably, I mean, we're probably rounding up the time for this, I suppose. What's your personal opinion on axions? If you were to give some betting odds on axions as dark matter, what does your instinct say? How much money should I put on it?
I might be biased, but yeah, I'm really open to any models at this point. I think we're just taking a step closer to these kind of scenarios, but it's still a long way because we have several assumptions that we made as well. Especially the large separation of scales is still unresolved here. So our results are based with what we can actually simulate with our computational resources. So we don't want to take this as a final answer. We want just to raise awareness to the fact that it might be different switching this parameter. But I wouldn't bet any money myself.
Don't have enough money to bet at this point. If we got a nice cushy postdoc somewhere, then I'll bet some money on the axions.
Exactly.
Is that your main morals and takeaway? Do you have any other lasting points you want to leave with?
I guess it would be interesting for more people to get interested in this kind of field. The code is publicly available, and I guess if more people would be interested in this setting, especially now that many people are skilled from a computational point of view. I wasn't, so I spent a lot of time learning what it takes to getting familiar at least with facilities and coding. But if people are interested, the codes are up, and there's many more applications that can be many more studies that can come out using cosmological codes. We're also planning to run further studies on n-body simulations. So that would be the sequel of this simulation. So we want to set up an initial conditions with the results from this simulation to an n-body simulation to capture the full gravitational dynamics of these mini clusters, like I said, that are bound objects. Do you
have any intuition for what you might see, or is it totally impossible to predict?
Well, I guess the structure of this mini cluster might change as well from the QCD axion values to n equals 0. And that means that maybe more at n equals 0, more axion might be lost, might be disrupted in a mini cluster, and therefore the distribution of those axions might be very different than at present day. That's very crucial for a direct detection experiment. If you have a previous result on n-body simulation show that 75% of the axions are bound in mini clusters, and the chance for us to encounter a mini cluster is very rare. So it's 1 in 10 to the 5. So if you're trying to detect axion on Earth, and most of them are in bound structure that you won't encounter, you're having a hard time to detect an axion. So I guess this is kind of an answer that needs to be a question that needs to be looked more carefully.
Yeah, 1 in 10 to the 5. That's not fantastic, I suppose.
Yeah, not at all.
I've been hogging the questions. Does anybody else have anything they want to ask Giovanni?
Can I ask one question? So thanks, Giovanni, for a very nice presentation. So here you stop at n equals 6 on that figure at the bottom left. Did you also look at larger n, which is kind of in the QCD axion range?
Yeah, that's a good point. For two reasons, we didn't look into it. The first is that what our colleague Javier has already done simulation at n equals 7. But also we need more computational power to look at larger n because of unphysical destruction of the main walls. So we would need, we use 3000 cube points. We would need more than that to study n equals 7 and n equals 8. So for n equals 8, you would need probably 8000 cube points. And we don't have the computational resources to run more than the average simulation with that resolution. So in order to make a comparison between different ends, we wanted to set up a similar resolution at least. And therefore, going over than 3000 cube and running order of 100 simulation would have been impossible with the resources that we had. Yeah.
Okay, thanks. Can you apply for more resources, or can you optimize your code further to go beyond?
I think the code is optimized to handle 8,000 cube. However, since we started this project in 2021, we didn't apply for resources this year. Fortunately, the university had its own allocation scheme, so we were able to enter the system with the national supercomputer and run our simulation there. And now we are definitely applying for 2022 for more resources next year. So probably we'll be able to do simulation with a higher resolution even.
Okay, sounds great. I have one more question. Can you go back to the excitons?
Sure.
Okay, yeah. So, so you mentioned that they break up kind of for a larger n, right? For n bigger than 2 into those smaller ones. So one thing what I noticed is that the size of those excitons in which it breaks up, that's always kind of roughly of the order of the inverse axion mass. That's something generic which you would expect.
Yeah, definitely. Exactly. So when the self interaction, when there's an instability region, the self interaction wins and tends to collapse the solution, and this reaches an equilibrium when you reach the axion component wavelength, because in that case you're saturating the axion potential. You can't go higher in the potential there, and you can't shrink further than that for that reason, because you're reaching the topological susceptibility and you can't go higher than that. And that's where the axion starts oscillating, because once you're saturated, you can only expand with gradients, but then you tend to collapse again, and there's this oscillation between expansion and contraction, which generates axion waves.
Okay. So that's the generic property, right? So that's
exactly. At the compton wavelength, you're saturating the potential. You can't shrink further than that.
So the question is, why do you then first form those larger objects for those larger n? So if I look on the left, the second plot from the left, there is first something which is larger than 1 over the axion mass.
Which plot are you referring to?
Okay, the bottom row, the second from left, tau equals 4.5, right? There is, in the beginning, there's a larger structure, is that, if I see that.
Well, yeah, exactly. So you're when you get into the stability region with a given structure, then you can only shrink up to the wavelength. So in principle, at the beginning they can be larger, but due to this instability region which develops at large n, you're likely to collapse and see the formation of smaller excitons later in the evolution.
Okay. Good. Thanks.
Hey Giovanni, hi. It was a nice talk because it was a great listen. I have a question about how I guess the simulation was run. So when I think about the general timeline for the evolution of the axion field, I think of two main components: the PQ symmetry breaking and the QCD phase transition. So, but at those kind of different two kind of times of the universe, I guess the universe is in a kind of a very vastly different kind of states. And so did you run kind of one very long simulation, or did you kind of break the simulation up into two components?
Yeah, that's a good question. We actually didn't break the simulation into two. So the ideal thing to do would be to, as you said, simulate first the Pei-Quinn phase transition, and then at some point stop the simulation because you can't go up to the whole physical range, and then start the QCD simulation. But in this thing, we just did the simulation in one hit, and we initialized the system where the strings are in the scaling solution as shown in the attractor solution of previous simulation. So we're trying to mimic what the configuration of the field would be in that attractor solution. But as I said, we can't really simulate the whole thing, so we had to make a choice of this sort. However, in here we are mostly looking into late part of the evolution, so how the whole topological defects network destroys and seeds excitons, and the whole non-relativistic field can be dark matter. So we focus more on the part where the network is destroyed rather than just the string network at very early times, much before the QCD phase transition.
So if you made it that far through, thanks for listening. This is probably going to be the last Dark Chatter for 2021. So hopefully we'll see you next year with a new series and maybe even in real life. Imagine that.
Thank you.